All right, guys, we're going to go ahead and get started with this first problem. It says a roller coaster with a mass of 1,831 kilograms rolls down a hill with an angle of 46 degrees from the horizontal. The coefficient of friction between the coaster and the track is 0.07. Cool. Okay, so we can see in our problem here that we have a roller coaster and it's coming down this hill. So technically this is like our inclined plane. So I'm going to go ahead and I'm going to draw that over here so we can really see what's happening. So here's my inclined plane or the hill of the roller coaster. Here's the angle that it's coming down at. It told me in the problem that that angle was 46 degrees. And then my roller coaster is just sitting on top of that hill right here. I know there's forces acting on my roller coaster. I know that gravity is pointed straight down. I also know that force normal is perpendicular from that surface. And I know that force friction points parallel in the opposite direction of motion. Something else that's super important about this problem is that since we're on an inclined plane, we're going to have to rotate our axes. So I'm going to make my y-axis point up perpendicular from that plane. So this will be the y. And then my x is going to point down parallel from that plane. And this will be the positive x. Number one says, what is the net force on the roller coaster in the x direction? Well, net force in the x direction would be the forces that point to the right. Well, as we can see here, we have our y pointing perpendicular and our x pointing parallel. But we have force gravity pointing straight down. So force gravity is actually in the x and the y. So we're going to need to split that up. So what I'm going to do first is I'm going to draw the y component of gravity. And the y component of gravity is going to look something like this. It's going to be in the same plane as force normal, except it's going to point straight down. So this is going to be force gravity in the y direction. The x component is going to be parallel to the plane, and it's going to point down the incline. So this is going to be force gravity in the x direction. How do I know that it points down the incline? The reason why I know that force gravity in the x points down in this case is because the object would slide down the incline if no other forces were acting on it and there wasn't any friction. The object would just begin to move downward. We've seen this happen before. Maybe we leave our laptop or something on our couch and we walk away for a second, and next thing we know, we hear a boom, and that laptop just went smack dab and hit the floor. Reason being, gravity pulled that laptop down our couch or down that incline because we probably placed it on the edge of the couch. So let's get back to solving for net force in the x direction. Net force in the x is going to be the forces that point to the right or in the positive x direction. In this case, that's force gravity x, minus the forces that point in the opposite x direction. That's going to be force friction. And this is going to equal mass times acceleration. Unfortunately, at this point in the problem, we don't have the acceleration, and we need to do some stuff to really figure out what force gravity x and force friction are. So let's go ahead and find out what force gravity x and force friction really are. Well, we see this triangle right here for force gravity, and we know that this triangle has some angle right here. And this angle actually is the exact same angle as the 46-degree angle over here. The reason being is that there is a math identity to prove this, but we're not going to take our time up now to show that. All I'm going to do is I'm going to expand this force gravity triangle over to the right. So as I expand this triangle out, I'm also going to rotate it. So let me expand this triangle right now. I have force gravity, and then I have force gravity in the y over here. And then I have force gravity in the x over here. I have this angle as well, because I know that this is a right triangle. So the force gravity that I've given over here is actually going to be my hypotenuse. The force gravity in the x is going to be my opposite side, and the force gravity in the y is going to be my adjacent side. The way that we find force gravity in the x is by doing some trig, and we find out that sine of theta is equal to force gravity in the x over force gravity. I simplify this and I get force gravity times sine of theta is equal to force gravity x. We should know that force gravity is really just talking about mass times gravity, so we can simplify that one once more and just write mg times sine theta is equal to force gravity x. This equation will always hold true when we are on an inclined plane. So I solve for it here, but I'm just going to keep taking this equation and using it on the next few problems. So let's just keep rolling with the force gravity because we just solved for it in the x, so let's solve for it in the y now. We see that force gravity y is the adjacent side. So that would be cosine of theta is equal to force gravity y over force gravity. Do the same thing that I did before, multiply force gravity over. So I have force gravity times cosine theta is equal to force gravity y. Substitute mg for force gravity, and I get mg times cosine theta is equal to force gravity y. Again, this equation will always be the case when I'm looking for the y component of force gravity. Now that I got these two out of the way, I can really start to dive into the problem. So going back to where we left off, at our net force in the x is equal to force gravity x minus force friction, let's go ahead and substitute this value for force gravity x. Doing so is going to give us net force in the x direction is equal to mass times gravity times sine of theta minus force friction. Well, force friction is really just equal to force normal times mu. And that equals mass times acceleration. We're going to see that we have another issue here, and that's that we don't know what force normal is. So let's take a pause right now, and let's go ahead and move on to question number 2. Question number 2 tells us that net force in the y direction is equal to the forces that point up, in this case force normal, minus the forces that point down. And by down, we mean down in the y direction, and that would just be force gravity y. This is going to equal mass times acceleration. Since we rotated our axes here, we can see that the roller coaster is not going to accelerate off the track. If it did, that would be very scary and not good at all. That's like some Final Destination vibes. So therefore, we can say that it is not accelerating. So if it's not accelerating, that means that our net force in the y direction is just going to be equal to 0. So that helps us answer number 2. And if we move on to number 3, it says, what's the normal force? Well, that's just going to tell us that normal is equal to force gravity in the y. We know that force normal is just equal to mass times gravity times cosine theta. We know what the mass is. It was given to us in our problem, and the mass was 1,831. We know what gravity is because we're on Earth, 9.8, and we know what theta is because that was also given to us in our problem, and that's 46. We can go ahead and solve really quickly for force normal. We find out that force normal is equal to 12,464.8 newtons. It's really important to note that the angle was given to us in degrees. So we need to make sure that our calculator is in degrees. Alrighty, now that we have force normal, we can finally go back to our net force equation in the x and solve for it. So net force in the x direction is going to be equal to mass times gravity times sine theta, because that's our force gravity x, minus force friction, which is force normal, which we just solved for, is 12,464.8 times the coefficient, which is given to us in our problem, and that's 0.07. So if we go ahead and plug in our numbers for mass, gravity, and theta, we get net force in the x direction is equal to 1,831 times 9.8 times the sine of 46 degrees minus 12,464.8 times the coefficient, which is 0.07. Solving for all of this and simplifying, we get net force in the x direction is equal to 12,035 newtons. Now that we've figured out net force in the x direction, we can go ahead and use that to solve for our acceleration. We know that net force is equal to mass times acceleration. So if we plug in, we get 12,035 newtons for our net force. Our mass was 1,831, and acceleration is what we're solving for. So if we go ahead and divide by mass now, we should end up with our answer for acceleration, and we find out that acceleration in the x direction is going to be equal to 6.57 meters per second squared. Since this is the first problem, I do want to take this time just to show you guys something really quick. And if we solve for it with variables, we can really see how mass on an incline is going to impact acceleration. So net force in the x direction is equal to mg sine theta minus force normal. Well, force normal was just equal to mg cosine theta times the coefficient, which equals mass times acceleration. We're concerned on how mass is going to impact acceleration, so we're going to take this part of the equation. By doing that, we see that mass times acceleration is equal to mass times gravity times sine theta minus mass times gravity times cosine theta times mu. You should notice that there's a mass in each variable. Therefore, we actually can see that mass is not going to impact the acceleration of an object on an inclined plane. If you don't believe me, I'm just going to go ahead and solve for this really quick with numbers to show you that very quickly. So gravity is 9.8, sine of our angle, which is 46, minus gravity again, which is 9.8, times cosine of our angle, which is 46, times 0.07. If you do the math here, we're going to end up with the exact same answer. And I still get 6.57 meters per second squared. So what does that tell me? That's just going to tell me that on an incline, mass will not impact the acceleration. The only variables that will impact the acceleration of an object on an incline are going to be gravity, the angle of the incline, and lastly, the coefficient of friction. This should go without saying, but obviously, as the angle increases, acceleration will also increase. And that's just because sine gets bigger and bigger as the angle gets bigger, cosine gets smaller and smaller as the angle gets bigger. A bigger sine means a bigger force gravity x, which means a bigger acceleration. And that's because as the angle increases, force gravity x is going to get bigger and force gravity y is going to get smaller. Since force gravity y gets smaller, force normal is getting smaller. Smaller force normal means smaller force friction. And if force friction gets smaller, it just means that we're going to have a bigger net force. Alrighty guys, back at it again with question number 2. Question number 2 says a block slides down an inclined plane with a constant velocity, interesting, of 10 meters per second. The block has a mass of 22 kilograms and the incline is at an angle of 12 degrees. So here's our box sliding down this inclined plane. Awesome. First thing we want to do is go ahead and draw our free body diagram. I'm just going to slap this free body diagram right on top of my box. We need to remember that we rotate our axes. So up or perpendicular from the incline now is our y-axis and parallel to it is our x-axis. Now that we have that taken care of, we can go ahead and draw our forces. Force normal points perpendicular from that surface. Force friction is going to point parallel and in the opposite direction of motion. And then force gravity points straight down like it always does. First question says, what is the net force on the box in the x direction? So we don't even need our free body diagram to figure this out. We just need to make sure that we were paying attention to the question. And we see right here it says constant velocity. Well, constant velocity is telling us that we are not accelerating. If we are not accelerating, we do not have any net force. Our net force is just 0. And that's because net force in the x direction is equal to mass times acceleration. Acceleration is 0, therefore our net force in the x direction is just 0 newtons. Let's take a look at number 2 now. What is the force of friction acting on the box? So now we are going to need to start paying attention to our free body diagram. So let's go ahead and break up gravity into its x and y components like we did before because we're on an incline and we need gravity to be in the y direction that we rotated and the x direction that we have now, which is parallel to the incline. That's going to give us a y that looks something like this, and I'll write FGY. And then our x is going to look something like this. Awesome. In case you forgot, the angle of the incline is right here. And just remember that this angle right here is going to be the same as this angle right here. So we already have the equations for force gravity x and force gravity y because we just did it in our last problem. And those equations told us that force gravity in the x direction, because it's the opposite side, is equal to mass times gravity times sine theta. And force gravity in the y direction, because it's the adjacent side, is equal to mass times gravity times cosine theta. So question number 2 is asking us, what is the force of friction acting on the box? To figure out the force of friction acting on the box, we're going to need to take our net force in the y direction. And we know that net force in the y is going to be equal to the forces that point in the positive direction, force normal, minus the forces that point in the negative direction. And that would be force gravity y, which we said force gravity y is just mass times gravity times cosine theta. All of this is equal to mass times acceleration in the y direction. For an inclined plane, we're not going to accelerate in the y direction because our box is not hopping down this incline, it's just sliding down it, and it's sliding down in the x direction. So the acceleration is going to be 0 here, meaning that our net force is 0. Since our net force is 0, that's just telling us that force normal is equal to force gravity y, mg cosine theta. So to figure out force normal, we just plug in our numbers into this equation, and we will end up with force normal. For this specific problem, I would get force normal is equal to the mass, which is 22, times gravity, which is 9.8, times cosine of 12 degrees. Make sure your calculator is in degrees here so you get the right answer. I find out that force normal is going to be 210.89 newtons. I did just realize that I skipped question number 2. It wasn't on purpose, I just looked over it, but let's go back to it really quick. Question number 2 says, what is the force of friction acting on the box? Great question. So we're going to use kind of the same approach that we did before for number 3 to figure out number 2. And that approach is going to be net force in the x direction is equal to the forces that point to the right. And since it's on an incline and it's moving down that incline, it's going to be force gravity x. So force gravity x minus the forces that point to the left. And that's going to be force friction. All of that is equal to mass times acceleration. But we already know that it's not accelerating, so we know that the net force in the x direction is also 0 newtons. So that's just going to tell us that force gravity in the x direction is equal to force friction. And we know that force gravity in the x direction is really just mass times gravity times sine of theta. So we plug in our numbers just like we did when we were figuring out force normal, and we find out that force friction is equal to 22 times 9.8 times sine of 12. That's going to give us a force friction of 44.83 newtons. Next question asks, what is the coefficient of friction between the box and the plane? Well, that's just going to be a piece of cake now that we have all of our other answers. And we remember that force friction is equal to force normal times mu. I just found out what force friction is. I know what force normal is. It's just plugging the numbers in. So I'm going to divide by force normal to get mu by itself. And I get mu is equal to force friction, 44.83, over force normal, 210.89. I find out that my mu should be equal to 0.21. Remember, mu is unitless. There's not going to be any units of mu, so it's just 0.21. Alrighty, now let's take a look at our last problem here where it says if the incline of the plane were increased to 26 degrees, what would the net force in the y direction be? This is a trick question because I'm giving you information, making you think that it's going to change, all that good stuff. But we know that objects on inclines do not accelerate in the y direction. Since there's still no acceleration in the y direction, the net force is still just going to be 0 newtons in the y direction. What would change, though, is net force in the x direction. Right now, we're moving at a constant velocity in the x direction, but if we increase that incline, we're no longer going to be moving at a constant velocity. How do I know that? Well, the reason why we will no longer be moving at that constant velocity is because force gravity x is going to be bigger than force friction. How do I know that it's going to be bigger than force friction? Well, force gravity x depends on mass, gravity, and sine theta. And force friction depends on force normal, which is mass gravity cosine theta. As our angle gets bigger, this is going to get bigger. As our angle gets bigger, this is going to get smaller. So we're going to have more and more force gravity, and we can see right here that as this number gets bigger and bigger, and this number gets smaller and smaller, our net force is going to get bigger and bigger. So yes, the net force in the y direction will remain at 0, but the net force in the x direction would increase. And what does an increase in the net force in the x direction do? It's going to make us accelerate. So it's going to increase acceleration in the x direction as well.